Until now, advanced chip making has been defined by two companies. TSMC manufactures roughly 90% of the world's most advanced chips. ASML is the only company that can build lithography machines capable of printing them. That balance held for a while. Now a new startup claims it can break both. Their new tool can print chips at the sub-nanometer scale in a single exposure at roughly half the cost. And here's the part that most people miss. They don't want to sell this machine. They want to build entirely new chip factories around it. And if this works, it doesn't just threaten ASML and TSMC. It puts the entire advanced chip manufacturing model at risk. Every breakthrough in microchips eventually runs into the same wall. How do you print it? Chip manufacturing uses hundreds of tools and thousands of steps, but one step dominates everything: lithography. This is an EUV lithography machine. It is the most complex and expensive manufacturing tool humanity has ever built. Its job is simple to describe. It prints transistor features onto silicon wafers. It actually defines how small, how dense, and how powerful chips can become. At today's leading edge, those features are just a few nanometers wide. See it for yourself. Here, we are zooming into a 0.2 nanometer chip by firing electrons. What you are seeing here features just a few nanometers wide. This particular transistor is more than 10,000 times smaller than a human hair. So how do you manufacture something so small with a machine so colossal, the size of a bus? And the answer is a light. You shine light through a mask onto a silicon wafer coated with light-sensitive chemistry. Where light hits, chemistry changes. Where it doesn't, material is removed. Layer by layer, a chip appears. That's how we turn sand into thinking machines. The idea is pretty simple. Making it work at the nanometer scale is not. As transistors shrank, light became the limiting factor. Early lithography used deep ultraviolet light at a 193 nanometer wavelength. It worked until physics stopped it. It turned out you can't reliably print features smaller than the wavelength you are using. So the industry made a radical shift to extreme ultraviolet lithography. EUV uses light with a wavelength of 13.5 nanometers, more than 10 times shorter than before. That single change, combined with a cascade of hard-won innovations, is what unlocked the most advanced chips on Earth. But EUV comes at a price. EUV light gets absorbed by almost everything: air, glass, lenses. That's why the entire system has to run in a near vacuum. To generate EUV, molten tin droplets are blasted with lasers inside a vacuum chamber. The light is then reflected using mirrors polished at near atomic precision. This took decades of research, much of it pioneered the United States. Today, only one company can actually build these machines: ASML in the Netherlands. And each tool costs roughly $400 million. And despite that price, the economics still work. A single EUV machine can generate over $600 million worth of wafers per year. The real challenge isn't buying the machine, it's making it work. And at the leading edge, only a handful of companies can do that reliably. The list is really short. It's TSMC, Samsung, and Intel. Which brings us to the real problem. As transistor nodes shrink, printing gets harder. Eventually, you can't print the smallest features in a single exposure. So the industry is forced to rely on a very complicated workaround. It splits patterns into multiple passes. This is so-called multi-patterning. Imagine drawing fine lines with a marker that is too thick. In this case, you draw every other line first, then you shift the grid and repeat. This lets us produce patterns at least 4 times denser than the original. It works, but every pass adds masks, costs, and defect risks. Costs rise fast, and this is a real killer today. To keep scaling alive, ASML pushed EUV even harder. The new version, High-NA EUV, still uses the same light but with far more aggressive optics. That enabled scaling beyond 2 nanometers toward the Angstrom era. These machines are already running at TSMC, Samsung, and Intel, but the cost is extreme. Each tool is approaching $500 million. The next step, Hyper-NA EUV, pushes EUV even harder. So instead of changing the source of light, They extract even more resolution from the same light by pushing numerical aperture. That makes the machines even larger, more complex, and, of course, more expensive. At some point, the machine becomes so expensive that the chip it enables stops making economic sense. Just think about it. By the end of this decade, leading-edge fabs are expected to cost $50 billion each. This will further concentrate advanced chip making in the hands of just a few companies with massive capital. Wafer costs are projected to climb to $100,000 per wafer. And at that point, advanced chips will become so inaccessible to smaller companies and new entrants. But what if the problem isn't how far we can push EUV, but that we keep pushing EUV at all? What if there is a better alternative? What if smaller features could be printed in a single shot at 1/10 the price? This is where Substrate, a US-based startup, proposes a different path. Instead of pushing EUV optics even harder, they are abandoning EUV entirely and betting on X-ray lithography. The idea isn't new. Researchers have explored it for decades. The execution is the challenge. X-rays have much shorter wavelengths than anything used in today's fabs, but they're extremely hard to control. For a long time, the optics simply didn't exist, and generating stable X-rays meant using synchrotrons. These were machines hundreds of meters long, often occupying entire buildings, not something you could ever put inside a factory. Inside a synchrotron, electrons are accelerated to almost the speed of light. Powerful magnets then bend their paths, and this motion creates bright X-ray light. What changed is not the concept, but the supporting technology. Over the years, the optics improved. X-ray sources became more compact and better controlled, and all this progress accumulated. Then Substrate pulled these pieces together. Instead of adding more masks and more steps through multi-patterning, they asked a simpler question. What if we stop increasing complexity and just print it all at once? You can think about it this way. EUV is like sketching a drawing line by line. X-ray lithography aims to stamp the entire drawing in a single exposure. Here, we are dealing with electromagnetic radiation in the range of a few angstroms, roughly 0.01 to 10 nanometers, which makes it up to 1,000 times shorter than the wavelength of EUV. That is ideal for scaling because it means you can draw smaller features. In practice, it's extremely difficult. X-rays pass through most materials instead of bending where you want them to, making them notoriously hard to control. That's why X-ray lithography lived in research papers for decades. The physics is elegant. Manufacturing has been hard. Substrate claims they have now crossed enough of those barriers to turn X-ray lithography into a real manufacturing tool. But how do you produce X-ray light inside a fab without building a particle accelerator the size of a city block? This is where things get really interesting. They're not sharing many details, but it appears they're using a compact particle accelerator directly into the lithography system. Not a kilometer-scale synchrotron, but something that actually fits inside a factory. Inside the system, electrons are accelerated to near the speed of light, using radio frequency cavities. Those electrons are then sent through precisely arranged magnetic structures. As they pass through those magnetic fields, they are forced to wiggle, and when electrons wiggle at these energies, they emit intense bursts of X-ray light. It's the same idea used in a synchrotron, just compressed by orders of magnitude to fit inside a factory tool. Substrate hasn't shared many technical details on the tool itself, likely for competitive reasons, but they have shared the results. And this is where the conversation shifts from theory to evidence. So far, Substrate has demonstrated printing of 12 nanometer features. Those are directly relevant for building sub-2 nanometer transistors. They also claim they can use single patterning for all layers, printing in one shot what today requires multiple complex passes. According to Substrate's data, they've achieved resolution comparable to ASML's most advanced high-NA EUV systems. When it comes to lithography quality, consistency matters. They report consistent feature sizes across the entire wafer, with accuracy down to about 0.25 nanometers, consistency measured in fractions instead of an atom. If these numbers hold, the implications are significant. It means we could pack more logic into smaller areas and print it all in one exposure, using a tool that costs roughly $50 million instead of $500 million. In practical terms, that translates to better chips for AI and mobile applications at dramatically lower cost. But at mass production scale, Tools have to run fast, all day, every day, year-round. And for EUV, it took more than a decade to reach that level of maturity. X-ray lithography would have to go through the same process. So Substrate doesn't plan to sell the tools. They instead want to build their own factory in America, install their own machines, figure out the recipe, and offer foundry services directly. That puts them in direct competition with TSMC and Samsung. This isn't about just inventing a new tool. It's about inventing an entirely new factory and new foundry model around it. And this will take at least another 5 years. This is where reality hits. There's a reason NVIDIA stays fabless and lets TSMC handle manufacturing. TSMC didn't just buy machines, they built recipes over decades of billions into yield learning and manufacturing discipline. That only pays off because of scale. TSMC runs around 30 factories and produces roughly 1.6 million wafers every month across many customers and products. That combination of process mastery, volume, and packaging is why matching or beating TSMC is so hard. So we'll see. This could be the start of a new era or a lesson in how unforgiving chip manufacturing really is. However, Substrate is not the only company working on particle accelerators as light sources. In the US alone, there's X-Light and inversion. Research is also ongoing in Europe, Japan, and China. But unlike Substrate, they're solving a different problem. Most of these efforts focus on the light source itself, generating brighter EUV or soft X-ray light to push existing lithography further. For example, X-Light is building a free electron light source designed to extend the UV. That fits into the existing roadmap and may help ASML tools go further, but it doesn't replace them. Substrate is aiming much higher. They're trying to replace the entire lithography step with a completely different tool, and then rebuild the entire chip manufacturing process around it. Thanks for watching, and if you want the real story behind the world's fastest moving AI breakthroughs, make sure to like and subscribe to Evolving AI for daily coverage.